Good morning, Dresden High School. All right, so number 9 is straight out of your textbook. It's a pretty easy example. I made up 10 to help you figure out 9. All right, so how I do 10 is basically how you do 9. Pretty simple. All right. Now, it says, what are the real and complex zeros? Your real zeros are listed. Your real zeros are right here. They're the x values or the x-intercepts. So your real zeros are x equals -1, x equals 0, x equals 1. I don't know how to explain that any easier. Right? We're going to synthetically divide them out. Now, this example, unlike the one above, needs a lot of placeholders. It's got gaps. There's a 0x to the 6th that's not there. There's a 0x to the 4th. There's a 0x squared. And it's also missing the constant at the end. So be careful about that. It needs placeholders. Whichever zero you divide out first doesn't matter. It really doesn't. But our coefficients are 1, 0, 2, 0, -1, 0, -2, and then a 0. Make sure I add 8 pieces. All right, I'm good. Now you can pick any one you want to do. I'm just going to start with the first one, the -1. And remember, you drop, you multiply, and you add. That's all you do. You drop, multiply, and add. So I drop the 1, I multiply, and I get -1. I add, and I get -1. I multiply, and I get 1. Something just seems wrong here. Drop, and multiply, and add. I add and I get 3. I multiply and I get -3. I add and I get -3. I multiply and I get 3. I add and I get 2. I multiply and I get -2. And you just repeat the process. I add and I get -2. I multiply and I get 2. I add and I get a 0. I multiply and I get a 0. And I add and I get a 0. And this last one is your remainder. All right? Last one's always a remainder. I'm going to repeat the process, but this time with a 0, because that's the next one. And I drop, and I multiply, and I add. And I multiply, because 0 times -1 is 0, and I add. 0 times 3 is 0, and I add. 0 times -3 is 0, and I add. 0 times 2 is 0, and I add. 0 times -2 is 0, and I add. And here's my remainder again. And I continue the process again, this time with a 1. So I drop, I multiply, and I add. 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 And there's my remainder again. So what have I done? I have reduced this thing down from a 7th degree polynomial to a 4th degree polynomial, something that will probably factor. This is my constant, my x squared, my x cubed, and my x to the 4th. This reduces down to an x to the 4th plus 3x squared plus 2, and its quantity is set equal to 0 because there's still 4 solutions here. And it actually does factor. You could also do the quadratic formula, but it factors as x squared plus 2 and x squared plus 1. Because x squared times x squared is x to the 4th. Add 2x squared, add another x squared, 3x squared. 1 times 2 is 2. And this is where the remaining zeros are. All right, because you're supposed to find all of them, real and complex. So you're going to use your zero product property. X squared plus 2 is 0, or x squared plus 1 is 0. You're going to subtract your 2. You're going to take your square root. And you're going to realize that that's not real, it's imaginary. Don't forget plus or minus. So x is plus or minus I root 2. You do the same thing over here. X squared is negative 1. X is the root of negative 1, plus or minus the root. So x is plus or minus I. Now your job was to use those zeros to completely factor over the complex number system. So here's a 0. The factor is x plus 1. Here's a 0. The factor is actually, oddly enough, x minus 0, which I'll clean up, because that's what we do. We take away. Here's a 0. The factor is x minus 1. We just take away whatever the 0 is. We have plus or minus 2i, and one of my factors is going to be minus I root 2, and the other one's going to be plus I root 2. You have the plus or minus I here, so one of them's x minus I, one of them's x plus I. And the only thing I'm going to do is I'm going to clean this up. X minus 0 is simply x. And it's kind of customary to put that up front. So x times x plus 1 times x minus 1 times x minus I root 2 times x plus I root 2, x minus I, and x plus I. And that is a complete factorization over the complex number system of a polynomial. They do make you do this in dual enrollment and pre-calc. They don't make you do it in bridge math. Keep that in mind when you choose your course for next year. Let's see here. It says try your best to do the following by hand. At the very least, one side them before using a calculator. So I'm going to one side. I'm going to look at 12. I have no idea what these are like. I pulled them straight out of your book. I'm just going to shift everything left. 2x cubed minus an x cubed is a singular x cubed. 3x squared plus an x squared is a 4x squared. What else we got? We got this 9x that's moving over, minus 9x. We got a minus 36. And this one definitely factors. Both pieces possess at least an x squared. Or at least the first two pieces. I'm doing factoring by grouping. If I pull x squared from x cubed plus 4x squared, I should have x plus 4 left. Now I notice that both of these pieces contain a negative 9. And if I pull that negative 9, by gosh, I have x plus 4 left. So, it was factorable. The common factor is x plus 4. The stuff left over is x squared minus 9. Try and make those connections there. And I can do a little more factoring. X squared minus 9 is that difference of two squares pattern that I've been preaching the last couple days. Factors is x minus 3 times x plus 3. So, there's my three answers. There's three of them. X is a negative 4, x is a 3, or x is a negative 3. That wasn't so bad. My guess is all of these factor nicely. Here, I'll even give you 13. If I move this over, I'd have a single x to the 4th. I would take away 3, so plus x squared. No reason to move the negative 12x. Oh, I forgot something, didn't I? Really messed that one up, didn't I? I have a negative 5x to... I have a single x to the 4th. Sorry about this. I have a negative 3x cubed. I tried to do something that Jacob Hoy would do there. And I have plus 4x squared. And then minus 12x. All equal to 0. That one also factors by grouping. I'll let you figure that out. All right. Solve the inequalities, and then I have the by hand question. Because you can. They're not too hard. So if I was looking at 14, which is probably a little easy. Oh, look at 16. 16 is the hardest of these. 0 greater than. I notice that the leading two pieces both contain at least a 4 and an x squared. Now if I pull it, I would have x plus 2 left. Now if I pull a negative 1 from this second grouping, I would also have x plus 2. Make some sense of that. Negative x minus 2. Now I'm going to rearrange. 4x, x plus 2 is the common factor. The stuff left over is 4x squared. I'm going to continue factoring. Hit it with an a squared minus a b squared pattern. And these are not x values. These are called critical values of x. Because this is an inequality. Inequalities are answered with inequalities. Like they're not answered with equal. But we actually do use the equal symbol here a little bit. A critical value, x subscript c of x, would be negative 1/2. A critical value of x, slide and divide, would be positive 1/2. And a critical value of x would be negative 2. So those are, I'm probably going to have 3 intervals here, maybe more, of solutions. I'm going to draw a number line. This is why kids hate inequalities, because you have to draw a number line. You have to go back to that little middle school skill. And I'm going to plot these points on there. I'm going to use an open hole because there's no equality. There's an open hole at negative 2. There's an open hole at negative 1/2. And there's an open hole at 1/2. And then I'm just going to play with the numbers. I'm going to test around them. I'm going to test things left, middle, right. I'm going to test a negative 3. So I'm going to go back to the original equation. I'm going to plug in a negative 3. And I'm going to say, is 0 greater than 4 times a negative 3 cubed plus 8 times a negative 3 squared minus a negative 3 minus a 2? Is 0 bigger than that thing? I kind of feel like it probably is. This would be negative 27 times 4, which is negative 108. This would be 8 times 9 plus 72 plus 3 minus 2. And is 0 bigger than that? For sure. That is true. Because that's going to be a negative number. So I get to keep everything here. In other words, I am negative infinity to negative 2. That's part of my solution. Now I'm going to test between negative 2 and negative 1/2. And I'm just going to plug in a negative 1. So is 0 bigger than 4 times a negative 1 cubed plus 8 times a negative 1 squared minus a negative 1 minus a 2? So that's going to be negative 4 plus 8 plus 1 minus 2. And this is going to be false because this is going to give me 4, 5, 3. So I reject this territory. It is rejected. Now I got to test between negative 1/2 and positive 1/2. And I'm going to plug in a 0. Now, I'm not going to write this out, but if I plug in a 0, that's 0, that's 0, that's 0, I get negative 2. 0 greater than negative 2 is true all day long. So I get to keep this little piece of territory right here. Negative 1/2 to 1/2 is part of my solution set. Now I just need to test something to the right of 1/2. So I'm going to plug in 1. So is 0 bigger than 4 times a 1 cubed plus 8 times a 1 squared minus 1 minus 2? Now this is going to give me 12 minus 3, which is 9. That's false. 0 is not bigger than 9. So I reject. So I only kept 2 things. My actual answer here is that I am the interval from -infinity to -2 union with the interval from -1/2 to 1/2. Or, if I like set builder notation, I could be all values of x such that x is less than -2, comma, -1/2 less than x less than 1/2. These are both valid ways of answering. And yeah, yep, that's how you do these. They're a good chunk of work. They are. I actually don't mind if you do them in a calculator, to be honest with you, but you'll have to understand your graphs. But that's how you do something like that by hand. All right, I got one more problem I'm going to do with you. Take me a quick little break, and I'll be right back.